Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. Okay, welcome to the Laplace transform chapter, lecture on the inverse Laplace transform, specifically how to do inverse Laplace transforms in practice. So, the inverse Laplace transform is a path integral in the S-plane, and it can be quite challenging to calculate. Therefore, software and tables such as that in the appendix given here are typically applied instead of using the definition. In system dynamics, it is common to apply the inverse Laplace transform to a ratio or products thereof of polynomials in S, like the one shown here. Okay, polynomial of S in the numerator, polynomial of S in the denominator. Sometimes there are multiple factors of these ratios of polynomials in S that are multiplied together. So this might be multiplied by another one. Okay. However, inverse transforms of general ratios, such as these, do not appear in the tables. Instead, low-order polynomial ratios do appear and have simple inverse Laplace transforms. Suppose we could decompose this into smaller additive terms. Due to the linearity property of the inverse Laplace transform, each transform could be calculated separately and consequently summed. The name given to the process of decomposing these ratios of polynomials in S into smaller additive terms is called partial fraction expansion. It is not particularly difficult, but it is rather tedious. Fortunately, several software tools have been developed for this expansion. The inverse transform with a partial fraction expansion in Matlab. Let's use the part_frac function to do this partial fraction expansion and then transform that into something that looks like one of our table identities, apply those table identities, and profit. That's the plan with this example. So what is the inverse Fourier transform image of this f of s, given here, ratios of polynomials of s multiplied together? All right, so I want to take you through the way to do this in Matlab using part_frac and then applying tables after that. So first, we define a symbolic variable in Matlab s. So of course, this requires the symbolic toolbox in Matlab. So sims s will declare it to be complex here. Now we can define f, a symbolic expression for our f of s. So we just type it right in. Now all that remains is to apply this part_frac function. So we just apply it directly to f. There are some other options that are optional and we choose not to use them. And we get this fraction coming back to us, which looks like a pretty simple fraction and a more complicated fraction. Okay, but notice they are additive, which was what the partial fraction decomposition, that was its main goal, was to do that for us. Now consider the Laplace transform table. What's this? The Laplace transforms table? Wow, all right, here you are. So this is the table, and we're going to look for the first term in here, because the first term was relatively simple. We're hoping that we can identify it in this table. So let's recall what that was. It was 13 over 3 times 1 over s plus 6. So that is this expression here. If we go over here and look for something that looks like this in the Laplace transform table. We scroll down. First we're seeing, here's just some properties. Like this is actually linearity right here. This is the linearity property. Here is the time shifting property. On the left we have the function of time. On the right we have the function in the Laplace domain. So Fourier transforms go left to right. Inverse Fourier transforms go right to left. And if we keep scrolling, we see the integral property, derivative property, convolution. We start to see some functions that we recognize: Dirac delta, unit step, unit ramp. Continue scrolling, and we notice that right here, the Laplace transform side has a 1 over s plus a, which looks a lot like our term, which is in fact some factor, 13 over 3, I think it was, times 1 over s plus 6. Now, the a equals 6 is pretty clear from here, as long as it's okay to have this factor out front, which we know from linearity that it is. This constant can be pulled out front. It is just an integral after all, so constants can be pulled from the integrand outside of the integral. So we can simply apply this inverse Laplace transform right there. So we've identified a to be 6, and we can just say, okay, here's our inverse Laplace transform. We have to scale the result by this factor out front. We've identified what a is, and we can immediately then write down that the inverse Laplace transform of this entire expression, through linearity we can pull out the constant, and through the table we can identify that the inverse Laplace transform of 1 over s plus 6 is just e to the negative 6t. So that's what we've got here. So that term we could treat separately, because when we apply the inverse Laplace transform to this entire expression, linearity applies, and we can do this term first, as we've just done. Bam. Okay. Now we're going to call this second term f2, and we're going to take a look at this, see if we can do something similar. It's actually going to be a bit more complicated, just messy, not really complicated. Okay, so it's not quite as obvious. If we look through the transform table for this term, it isn't quite as obvious. So we look for something that is as close as possible to it, and it's this preimage of the inverse Laplace transform. It's this transform. So if we go over and take a look at it, this shows up in the table. If you keep scrolling, it looks a little bit like this one. Okay, so our f2 is a little like this, but it's not quite this. So what we're going to try to do is write our f2 in this form so we can take this inverse Laplace transform in the table. Okay, so that's our plan. Going back to the text then, let's first make the numerator match. So this is going to be a lot of essentially algebraic massage, I would call it. Algebraic massage, where we try to make one expression look like the other expression. Of course, we can't violate any algebraic rules as we do that, but if you multiply something here, you have to divide it somewhere else. If you add something here, you have to subtract it somewhere else. That's what we're going to be doing. We're essentially trying to massage this f2 into this form and see what happens. So we look at the numerator first. The numerator is, if you look at this expression a little closer, it is 5 over 3 times s minus 24 divided by s squared plus 6s plus 36. So it doesn't look exactly like this because we have to get a 1 as the coefficient of s, and we also need to do some sort of completing of the square where we have s minus a squared here and an s minus a in the numerator. So we don't quite have that situation, so we're going to have to do some massaging here. The first thing we can do is we can make the numerators match. So it's easy to make this look like s minus a in the numerator. All we have to do is factor out a 5 over 3. So let's do that first. Factor out a 5 over 3, and we get s minus 72 over 5. Okay, so we're going to call this A1. And this A1 is going to be our first A that we have identified when we've tried to turn this expression, or turn our F2, this, into this expression. So it's our initial A that we've found. All right, so this A works for the numerator. And we would like for there to be a term in the denominator now that also looks like s minus a1 squared, right? For it to completely match, it needs to have that same s minus a squared. Those have to match. So we need to see if we can make that happen in the denominator. Asserting that there is an equality here, we're going to set that denominator, so s squared plus 6s plus 36, is what the denominator of f2 was equal to, right? It's just this denominator here. We want that to look like s minus a2. We don't know for sure if we're going to be able to succeed. We would like a1 to be here, but we need to figure out if a2 is going to equal a1. That would be our ideal situation. We would succeed at making a2 equal a1. We'd have that table quantity. But when we assert this equality, we are going to have to discover whether or not a2 is in fact equal to a1. So a2, omega are the two unknowns here. We expand out this right-hand side, and this right-hand side gives us coefficients that must be equal on the left-hand side polynomial and the right-hand side polynomial. So the s to the 0, or just the constant term in each side, they have to be equal. So that gives us that omega squared has to equal 36, this term, minus a2 squared. So we said that this term has to equal this term, and then we said that omega squared has to equal this. Great. If we equate the s coefficients, so that would be 6 and negative 2a2, then we get a2 equal to, we can directly solve then for a2, it's equal to negative 3, okay? That is not 72 over 5, right? That we solved for a1 before, and a1 was 72 over 5 for the numerator. Our a2 that we got in the denominator came out to be negative 3. That is not equal to a1, so no cigar, okay? We were hoping that this was just going to work for us. It didn't work because if we try to put the numerator in this form, we could. If we try to put the denominator in the form, we could, but we couldn't get the same a's to match, right? The a in the numerator and the a in the denominator didn't work out. So we have an a1 and an a2. We need to decide what we're going to do next. We can't make this polynomial fraction, we can't make our f2 match this exactly, okay? Unfortunately. It would be nice if it did, but it doesn't quite work. So what we do is we say, okay, well, the denominator one was a little bit harder. So what if we force this rule by using a new a1? So we could have changed a2 or a1, but let's change a1 to some new value. Okay, so a1 prime. So I'm going to give some new a1, the numerator a1, and we're going to call that. We're going to say that one has to equal a2. Okay, we're going to force this rule to work for us, and then we're going to deal with the consequences of that. So we force it by adding a term and also subtracting that same term elsewhere. Of course, you can do that. It sums to 0 if you add something and then subtract it. So you're allowed to do it. So we need a1 prime, our new a1, to equal -3. So if we add and subtract a term, this term, okay, so 5/3 a1 minus a1 prime divided by s minus a2 squared plus omega squared. So this is the term that we're going to add to our f2, okay? So let's add it to our f2, which is what we did here. And then we know we have to also turn around and subtract it, right? Because we can't change the value of f2. So we added it and we subtracted it. So now, by construction, when we add these two terms together, we're going to get an expression that matches perfectly this table value, all right? So we've got this extra term that popped up, but at least we've forced that one term to work for us. So here we go. This is, by construction, we chose this numerator to make sure that this happened. So when we add these together, look what happens. You're adding two fractions with a common denominator, so you can simply add the numerators together. We have 5/3 s minus a1 plus 5/3 a1 minus a1 prime. Well, the a1 here and the a1 here, they're both multiplied by 5/3. This one's negative, this one's positive. They cancel each other by construction. And the other term is left over. So we have s minus a1. Everything's multiplied by 5/3, so we can factor that 5/3 out. And you're left with 5/3 s minus a1 prime divided by s minus a2 prime, or sorry, a2 squared plus omega squared. We have this term, the subtraction term. So this guy these two absorbed together. This guy's still left hanging out here, so we have to make sure we remember it's there. Remember, we designed this so that a1 prime is equal to a2. So we now have this left expression is exactly what we need. So now this is the expression, and this first term we know is in the transform table. The second term we want to look at. So it could be the case you do something like this. You force one expression to equal something. The other expression could end up causing a new problem. It turns out when you are making something that looks like what we're dealing with into one of these terms, this is actually always going to work out. But it's not guaranteed beforehand. That's just something that does happen in these instances for a class of problems that looks like this. So we weren't just wandering off into the dark, fortunately. There is going to be a good thing that's going to happen. So we know this term is all good. We're good with this term. This is the term that's unknown still. So the second term is close to this transform image that we see in the table. So let's look at the table and find it. It's right next to the other one. Okay, so the inverse Laplace transform of this is given here. So one of the terms we made look like this. The other one's going to look like this, but we still have to do some rearranging of this term before it's ready. So let's do that. We've got, let's take a look here. So we must make the numerator equal to omega. So this numerator has to equal omega according to this form that we've got. Our omega, so our omega squared is 27, so our omega is plus or minus the square root of 27. The current numerator is, if we plug in a1 and a2, 29, okay? 29 is not plus or minus the square root of 27. Okay, so that would have been magical if it had just popped right out, but it didn't. So we have a term in our numerator that's 29. So this right here is 29, but we need it to equal, so it's not equal to, we need it to equal either plus or minus the square root of 27. And so we need to make that happen. Of course, one way to do that is simply force it to be that by factoring out 29 over the square root of 27. That makes omega square root of 27. And we have this form just as we constructed it to be. So returning to F2, we have arrived at this expression. We have a 5/3 factor multiplying something that is in the Laplace transform table, and we have negative 29 over the square root of 27 times something that is in the Laplace transform table. So now we can take the inverse, we can apply linearity so that we take the inverse Laplace transform of F2. The 5/3 comes out because it's a constant. 29 over the square root of 27 comes out because it's a constant. Now we have the, and the sum here is we can take the Laplace transform of each term because of linearity. And we are ready to take these inverse transforms, which is to say we're ready to just march from left to right across this table. We have this situation, we have this situation, so we're just going to march those from right to left across the Laplace transform table, and that will give us these two terms in our solution. So let's do that. The inverse transform is of F2 is the inverse Laplace transform of this term, which we see here, and the inverse Laplace transform of this term, which we see here, and then the linear combination of them as we've seen previously. So that worked out well. Okay, simple, I mean, more or less. Putting it all together then, so we also had that first term that we had way up here that was relatively easy to deal with, and that was this guy. So we have to combine this with our F2 solution. So we do that. And so we get that first term that we got plus the inverse transform of F2. Uh-oh. This is clearly wrong. It's not f of s, it's a function of time, right? F of t. Okay. I'd like to say that was on purpose to see if you caught it. Totally a mistake on my part. Okay, so you may have noticed during this example that even with Matlab's help with the partial fraction expansion, which remember Matlab did for us, we didn't even do that part. That's another whole tedious aspect of this problem. The inverse Laplace transform was a bit messy. So this is going to motivate you to learn the technique in the next section, which is just clubbing it with Matlab, okay? Or Python or whatever, but we're going to use Matlab. Sometimes we can just use Matlab or a similar piece of software to compute the transform in its entirety without having to worry about the tables and all that. Matlab's symbolic math toolbox function for the inverse Laplace transform is iLaplace, and for the Laplace transform, which is easier to compute without Matlab, so we aren't going to look at that, Laplace. Help iLaplace will give you the documentation, at least the abbreviated documentation. So let's apply this to the example above. So we have the same expression, and we would like to know what the inverse Fourier transform is. So use Matlab's Laplace is the instruction. We do the same thing we did before. We define a complex symbolic variable s. We define f of s. And then we simply club it with Laplace. Okay? And there are some options here that can help in certain instances. Maybe it's not evaluating, or maybe it's giving you a messy expression back. Sometimes you can use some of the optional arguments of Laplace, but in this case, it does a great job with the expression we give it, and it gives this inverse Laplace transform here, which is a little hard to parse. It's written in sort of a coded form, but if we look at it closely, we see that it's actually equal to our previous result, which is 13 over 3 e to the negative 6t. That one's easy to see. That's this term here, right? Plus, and now we've got this exponential is factored, and so is this 5. So we have 5 e to the negative 3t. 5 e to the negative 3t shows up in both of these terms. At least the e to the negative 3t does. So we factor that out. We factor out the 5 too, which I wouldn't have done, but Matlab did it. This is one of the things with symbolic packages. You can't always choose what they're going to do. So on the inside then, you've got cosine 3 root 3t, sine 3 root 3t. That looks good. The sine has a negative sign. Good. And now it just comes down to the coefficients. Are they correct? So first of all, there's a 5, and there's actually way at the end of this an over 3. So everything is 5/3 e to the minus 3t. So this first term, 5/3 e to the minus 3t, that one's good. So cosine has no coefficient other than 1 there. Now we have to make sure that that jives with this coefficient here, which is a little harder to see. We have 29 times the square root of 3 here, whereas we have 29 over 3 root 3. And we are then going to factor out 5/3, so we have to multiply by 3/5. The 3's cancel. The 5 is also an issue. Oh, yeah, the 5, there's another 5, or there's a 15 here. Shows up. So in the end, it does work. It's just a little bit harder to see that for the sine coefficient. So that's that. The inverse Laplace transform is actually pretty easy in many cases with MATLAB's symbolic toolbox or some other equivalent package. SymPy will do it too. But if you run into one that it doesn't just do for you, then you're going to have to figure out how to use the tables and or use the original definition if needed. So yeah, that's how to use the inverse Laplace transform, and how to take the inverse Laplace transform in general. So partial fraction decomposition, we're not doing it manually. I think that it's subtle and takes, it'll take a little bit of time to learn it. It's worth going through. It's an appendix in the Rowell and Wormley text, which I recommend. We're not going to slow down and learn that in detail. We learned how to use MATLAB's part frac to do the partial fraction decomposition instead. Great. And then we figured out how to use the tables, the first example, along with part frac. And now here we're using just Laplace to find the inverse Laplace transform. All these are really valid and practical tools for finding the inverse Laplace transform, which tends to be much harder than the Laplace transform. So yes, I will see you guys next time. Take care.